Hey everyone, and welcome to the AI Research Roundup. I'm your host, Alex. Today we're digging into a paper titled LTX-Video, Real-Time Video Latent Diffusion. The core idea here is a new transformer-based model for video generation. What's interesting is that it takes a more holistic approach, basically integrating the video compression part, the VAE, and the denoising transformer part together, rather than treating them as separate steps. They achieve really high compression, which helps make generation super fast. Faster than real time, in fact. Okay, so taking a look at figure 1 here, we can see some examples of what LTX-Video can actually generate. The first row shows a text-to-video example, a guy in a forest, and the other 2 rows are image-to-video, starting with an initial image and generating the rest of the sequence, like the car driving or the animated character dancing. These really highlight the kind of visual quality and motion fidelity the model achieves, even with that high compression and fast generation speed we just talked about. It shows pretty good adherence to the prompts too. So building on those examples we saw, figure 2 gives us a better look at how the denoising process actually works. Remember we talked about that holistic approach? Well, this figure illustrates that. You see, it starts with noise in that highly compressed latent space. Then there are several denoising steps happening purely in the latent space. That's the latent-to-latent part. But then, for the final step, the VAE decoder takes over and does both the conversion back to pixels and the final denoising. This helps bring back fine details and avoids a whole separate upscaling module. Okay, so digging a little deeper now into that VAE component we just talked about. Figure 4 actually shows us the architecture. On the left, you see the causal encoder. This is what does that really high compression, using things like 3D causal convolutions and downsampling blocks to get to that small latent representation. Then, on the right, we have the denoising decoder. This shows more clearly how it works. You can see the upsampling blocks, but also importantly, the noise injection points and the time step conditioning feeding in. This is how it handles that final denoising step we saw conceptually in the last figure. Right, so we've seen how the VAE compresses the video and then helps with the final denoising step. Figure 6 now shows us the core transformer block that actually works on those compressed latents. This builds on an existing architecture called PixArt Alpha, but with some key changes. For instance, it uses rope positional embeddings for better spatial and temporal understanding, and RMS norm instead of layer norm. You can also see the standard self-attention and cross-attention blocks here, with the cross-attention taking in the text prompt information. And that time step conditioning we talked about feeds in here too. Okay, so we just looked at the LTX-Video transformer block. Table 1 here puts that into context by comparing its specifications against several other video generation models. TXA, what really jumps out is that VAE compression we keep mentioning. LTX-Video achieves a total compression of 1 to 192, which is significantly higher than the others listed. This translates to a much better tokens to pixels ratio too, 1 to 8192. And, well, it manages this with a relatively compact 1.9 billion parameter model, smaller than some competitors. And, importantly, it doesn't need a separate upsampling model, which again helps with that speed. We've talked about the model architecture and its overall performance. Figure 9 here shows us specifically how the image-to-video generation works, particularly when you give it a starting frame. Remember we saw examples of that earlier? Well, this diagram illustrates the process. You see the input frame. It goes through the VAE encoder we looked at, which creates tokens. But importantly, these tokens for the first frame are given a special low time step, basically telling the transformer this part is already clean. The rest of the tokens start noisy, and the transformer then generates the video sequence starting from that initial conditioned frame. So, building on that image-to-video mechanism we just discussed, Figure 15 here gives us some hard numbers from human evaluations, comparing LTX-Video against other models. What we're looking at are pairwise win ratios. Basically, each row shows how often that model was preferred over the others. And, well, you can see LTX-Video in the bottom row. It consistently scores really high win rates against OpenSoraplan, CogVideoX, and Pyramid Flow, both for text-to-video on the left and even more so for the image-to-video task on the right. So yeah, those human evaluations really underscore the quality LTX-Video achieves, especially starting from an image. I think the big takeaway here is that combination of incredible efficiency, that high compression we saw, with really strong generation quality. This work really pushes us closer to real-time video generation that's actually usable, perhaps even on consumer hardware down the line. Well, that's all the time we have for today. Thanks for tuning in to the AI Research Roundup. I'm your host, Alex.